Hey, good evening and welcome back to AP Stats Notes Online. We've covered the basics of significance testing. And so now we're going to move into section 9.2, which gets us into testing specifically for a population proportion. Okay? And so first things first, it's an inference procedure, and there are some certain conditions that need to be met before we know that our inference procedure is going to give us any kind of valid results, right? So what are those inference procedures? What are those conditions for our inference procedures? And could they possibly be different? Well, it comes from the same place, right? Random, right? Our data must come from a well-designed random sample or random experiment. Right, one, it allows us to make inferences, right? If we're randomly sampling, then we can project our conclusions onto the population. And if we're randomly assigning treatments, then we can make inferences about cause and effect. So we do need to make sure that our data is coming from a random sample or randomized experiment. We have to state that in our condition check. We'll get to that in a minute. Normal. We want, especially in terms of proportions, right? We want to be able to use what's called the normal approximation. We want to be able to say that our sampling distribution is going to look approximately normal. And so the sampling distribution of the statistic is approximately normal. We can use that normal approximation as long as both n times p and n times 1 minus p are bigger than 10. Remember that these were successes and failures that we would expect to get out of a sample, right? Now, here's the only difference between intervals and tests, right? In confidence intervals, we don't have a population proportion. We don't have a P. We don't have any idea of what it might be. And so we use an interval to estimate that. Here we're testing a P. And so we actually have a p-value. So since we're assuming H0 is true, we want to use that p in our calculation here instead of p hat. If the null hypothesis is true, this is the number of successes and this is the number of failures we would expect to get out of a sample. Okay? So we're back to using p instead of p hat. And the moral of the story here is anytime you have a p to use, whether it's known beforehand or it's a claim or whatever, then use that in this normal calculation. If you don't, then you're going to have to use p hat. Okay? But we're still checking that they're bigger than 10. And that will get us into an approximately normal sampling distribution. Okay? And the last one is independent. We want our individual observations to be independent. We don't want the success rate to change from individual to individual. Even though we're sampling with replacement, we know that's going to happen. We just don't want it to change too much. And so we're going to check our 10% condition again. And again, it needs to come out of the form of an assumption usually. We're going to assume this many in our population, or we're going to assume that this sample size is is smaller than 10% of our population. Okay? So a lot of it sounds the same. The only difference is that normal check where we have a P or at least a claim to a P to use, and so we'll use that. Okay? All right. Next, what is a test statistic? Okay? What does it measure? The definition of a test statistic, and it's going to sound a little bit like a critical value, or at least the way we find it is going to be a little bit like a critical value. But here's what a test statistic is. It measures how far in standardized units, that's how it's going to look a little bit like a critical value. We're going to have to standardize it. But in standardized units, it measures how far a statistic deviates from what we would expect if H0 were true. Right? Basically, how far is your population, is your sample statistic from the claim to the population parameter? And we want to talk about how far away it is in terms of standardized units. Not just, it's 5% away, and so that must be our test statistic. No, it's all relative. How far away is 5%? Well, we need to do that in standardized units. And so we have a way to do that. And it gets us into the form of your standardized unit that is in the formula packet for you. On page 3 in your formula packet, the page that has the tables with your inference standard deviation calculations, at the top of that is a place that reminds you that a test statistic, basically we need to find out how far a statistic is from the parameter, so we're going to subtract those guys. And then we got to do it in terms of standard deviations. A z-score, which is basically what we're doing, this is basically a z-score, tells us how far two things are away in terms of standard deviations in standardized units. Okay, and so we have to divide by the standard deviation of the statistic. Okay, you know, the conditions that we checked before are all tied to this as well. Your independent check is what allows the standard deviation calculation to be accurate. The fact that we're finding a z-score has more meaning if we're using the normal approximation to a sampling distribution, right? And then our random sampling is what makes the statistic a good calculation, right? So that's what a test statistic is. And so we want to know, and in a test, we're trying to figure out, you know, assuming that the parameter is what is claimed to be, or assuming that the parameter is not different than, you know, for one population than it is for another, then how likely is it that we would get our statistic, our sample statistic, and we need to find out how far away it is in terms of standard units, okay? And that gets us into our one sample Z test, right? Our one sample Z test. It's a lot like our one sample Z interval. We call it a Z test or a Z interval because our test statistic is going to come from a normal curve. There's no reason why it shouldn't. When we get into testing means, we'll be back into using the standard deviation of a sample to create this test statistic. And so that will get us into a t-distribution again, but we'll worry about that in the next section. All right? What are the 4 steps for conducting a significance test, which is required in each step, right? We're into our state, plan, do, conclude again. And again, some of you want to maintain that labeling, state, plan, do, conclude, and I think that's a great idea. Some of you guys are going to set that aside and just think through what needs to be included in your test, right? And so state. We want to define the parameters, state our hypotheses, and then also let the world know what significance level you're going to use, okay? And we'll show all this in just a second. Plan it out. What inference method are you going to use? And go check your conditions. Okay, make sure that you do so specifically enough that it makes sense and that everyone knows what it is that you're talking about. And then go do it. Perform calculations. You want to include showing what your test statistic is, showing where this comes from, and showing your p-value, whether you choose to sketch a normal curve and use normal CDF, or if you choose to take that test statistic into table A, because it is just a z-score, and find that probability that a statistic will be this, assuming that the null is what it's claimed to be. Okay, that's what we're looking for in the p-value, is a probability. And then last but not least, of course, we want a good conclude. We want to interpret the results in the context of the problem. And we'll do that in 2 steps. One, we'll talk about, are we rejecting or failing to reject H naught? Right? This is going to come in 2 steps. Are we going to reject or fail to reject? And I'll just write fail to reject H naught. And then we will talk about, do we have enough evidence? We have evidence, or we do not have enough evidence to support H sub A, to support our alternative hypothesis. Okay? And that is going to be our procedure for a one sample z-test. So let's take a look at one. In actually just a couple minutes. Sorry, we've got a couple more things to talk about. What test statistic is used when testing for a population proportion? Well, this should all look very familiar and make sense, right? Our statistic, when we're talking about proportions, is going to be p hat. Our parameter is going to be that claim to p, right? And then our standard deviation of the statistic, if you look in your blue formula packet on that third page, it will remind you that we take p times 1 minus p, divide that by n, and then square root it. We're back to using p instead of p hat. Why? Again, because we have a claim to p. We're assuming that h naught is true. We're assuming that p is equal to this value, so why not use it? Okay? For our intervals, again, we use p hat because we didn't have any idea or any claim to what p actually was. Okay? The next question. What happens when the data don't support h sub a? And I've thrown that out there before in class in that, let's say that the claim to a population parameter is 0.75. And you think that the actual population parameter is less than 0.75. You take a sample and you get a p hat of 0.8, which is actually greater than 0.75. Then you don't even have data to support your alternative hypothesis. So why in the world would you go do a test, right? We're not going to put somebody on trial with absolutely zero evidence. We're not going to do it. So you need to look and see if the data even gives you any evidence at all against the null or to support h sub a. If it doesn't, then you move on. You're not going to worry about it. Okay? But if it does, we're going to go ahead and perform our test. Okay? Next question. Can you use your calculator for the do step? You absolutely can. I will show you this in the next class period. There's a technology corner on page 555 and 556 that walks you through how to do the test. Feel free to look at that as well. Okay? But for this next example of a test, I'll walk you through the calculation portion of that at the beginning of class. All right? Now, if you do the calculator, if you use the calculator, and it can be a very quick way to get what you need, you still have to name the inference procedure, you have to report the test statistic, and you've got to state what the p-value is, and I'll show you how to do all of that in class. Okay? All right. So, example for you. Water everywhere. Due to global warming, is the true proportion of water on the Earth's surface higher than the estimated 71%? Okay? The polar ice caps melting, and now we have more water. Well, what happened was scientists took samples from 50 different points on the Earth's surface in order to go test this, right? And so, here's how that test probably looked. Okay, first, state. This is how you need to show your state step, right? We want to test the following hypotheses at an alpha of 0.05 significance level. So our alpha is 0.05. If you don't want to write significance level, that's fine. You say alpha is 0.05. Now list your hypotheses. H naught, P equals 0.71. It's the statement of no difference. We think that the water, the proportion of water on the Earth's surface is higher than 0.71. Our statement of no difference is that it is equal to 0.71. Our alternative hypothesis is that the proportion is actually higher than 0.71. And tell everybody what P stands for. P is the true proportion of water on the Earth's surface. You need to write that out, state that out. Okay? Next is our plan step, right? List your inference procedure. What are you going to do to try to answer this question? I'll perform a one-sample z-test for a proportion. And now go check your conditions. Random. Well, they chose 50 random points on the Earth's surface, and so that satisfies the random condition, right? Normal. Well, remember that our normal comes from n times p and n times 1 minus p. Now, unfortunately, we're not going to have just the number of successes and failures like we did in the interval situation, right? we have to actually calculate out how many successes and how many failures we would expect to get if the null were true. So out of a sample of 50, if the null were true, if P really was 0.71, then we would expect 35.5 successes and 14.5 failures. Both are bigger than 10. Therefore, let me get this pulled down. The sampling distribution of P hat is going to be approximately normal. Okay? And that's what that's tied to. The sampling distribution of P hat is going to be approximately normal. We can use the normal approximation. And then, of course, independent. There are certainly more than 500 points on the Earth's surface in which they could have sampled to find the proportion of water. Okay? All right. And that takes care of our plan step. Do. Okay? And let's say that they found 38 points that had water, that were water, right? And so let's write this in here. So you need to write out your P hat. My P hat is 38 out of 50, which is about, you divide 38 by 50, it's about 76%. Okay? Which is higher than 71%. So it makes sense to do a test, right? If you did your sampling and turns out 22 of those points contained water, then your P hat would be 44%, and we wouldn't have enough evidence to even think that the proportion is higher. So we would not keep going with the test. But here we do. And so let's go find out in terms of standardized units how far away 76% is from 71, right? In other words, our test statistic. So it's a Z. It looks like a Z-score, sounds like a Z-score, feels like a Z-score, so it must be a Z-score. And so we want to make sure we're using our proportion in here in terms of a decimal. Okay, so 0.76 minus 0.71 all over, and then the square root of, again, P times 1 minus P divided by sample size, right? When we do that calculation, and I'll do that for you real quick. And that standard in that Z-score should be about 0.78. Okay? At which point, this is a Z-score. You go into table A, find 0.78. We're looking for, right, and we can sketch this out. I want to know, assuming that this is 0.71, right, we're going to assume that the P is 0.71. And the standard deviation here is 0.064, right? So then to get to 0.76, I got to go here and add 0.774, right? So 0.76 would reside about right here, and I'm looking for evidence greater than. I'm looking for this guy all the way out here. Okay? So it's going to be a pretty decently sized p-value here. Okay? So we can go to table A and look for 0.78, subtract that value from 1, or we can go into normal CDF, right? And so we're looking for Z being greater than 0.78. Normal CDF, and if you're going to use the Z-score, and you can, then let's see, you're not going to do this. What is that? You're going to go lower bound, oh I see, lower bound, which is 0.78, upper bound, which can be 100, mean of 0, standard deviation of 1. Now you can always go back to the actual setting, but this makes enough sense to get into the standardized set of z-scores, and where your mean is 0 and your standard deviation is 1. And when you do that, okay, you get, and I'll do that calculation for you real quick. You get a value of about 0.218, which means that your p-value is about 21.8%. Okay? Which means that assuming that 71% of the Earth's surface is water, that there's about a 21.8% chance that a sample of 50 points would result in 76% of those samples containing water. So now we're ready to conclude. And so our conclusion will look something like, okay, this. Since the p-value is 21.8%, sorry. Since our p-value is greater than alpha, right, and we want to show that 21.8% is greater than 0.05, then we will fail to reject the null hypothesis. There isn't convincing evidence to conclude that the proportion of water on the Earth's surface is greater than 71%. Okay? We need to show the comparison of the p-value to the alpha. Say that it's greater than alpha or less than alpha is great, but also show that in terms of a parenthetical if you want to, or just explicitly somewhere is fine too. Okay, and that's top to bottom a one-sample z-test. Now, if you're to use the calculator, then life can be a little bit shorter. And like I said, I'll show you in class exactly what that would look like, and we can even talk about some of the things that you can get rid of if you use the calculator. Okay? That's it for now. We do need to talk about a two-tailed test and how you get the p-value through a two-tailed test. We'll take a look at that in class as well. That can be a quick conversation and then get you into the homework. Okay? Have a good night. We'll see you guys next class period.